This is the pre-calculus video for section 4.8, day 2, which we're covering on March 12th. And we still had that objective of working with simple harmonic motion, so that's where we're at, solving problems involving simple harmonic motion. And it says, because of their periodic nature, the sine and cosine functions are helpful in describing the motion of objects that oscillate, vibrate, or rotate. For example, the linkage in figure 4.94 converts the rotary motion of a motor to the back and forth motion needed for some machines. When the wheel rotates, the piston moves back and forth. So what generally happens is we have some kind of mechanism in the vehicle that squirts a little bit of gas inside the chamber and then ignites it. And when it ignites that fuel, then there's a little mini explosion that pushes that piston. And so then it gets the back and forth motion going, and that's how most basic small machines are going to work when they're gasoline driven. If the wheel rotates at a constant rate omega radians per second, the back and forth motion of the piston is an example of simple harmonic motion and can be modeled by an equation of the form D equals A cosine omega t, where omega is greater than 0, where A is the radius of the wheel and D is the directed distance of the piston from the center of oscillation. So we need to remember that this A stands for the radius, and that our little omega here is going to be radians per second, because that is angular velocity. So we have a nice little simple harmonic motion formula to take a look at, and we see down in the drawing underneath figure 4.94, it says a piston operated by a wheel rotating at a constant rate demonstrates that simple harmonic motion. Now, let's take a look at the picture a little bit more, and I know some of this is really small, but there is our A value right there, the radius. And we see that along with the omega, angular velocity, times the time gives us a little circular drawing there. And that's how we connect all of this up to our simple harmonic motion. And they're showing us that we have this initial position of time at 0, and then the piston is going to move back and forth and back and forth. So for the sake of simplicity, we will define simple harmonic motion in terms of a point moving along a number line. So simple harmonic motion, a point moving on a number line, is in simple harmonic motion if its directed distance d from the origin is given by either d equals a sine omega t or d equals a cosine omega t. And we know the difference between the two because we've talked about it in class, that sine starts at 0, 0 or on the axis, and cosine starts high. So whenever we start high or low, then we want to go ahead and use cosine. So simple harmonic motion where A and omega are real numbers and omega is greater than 0, the motion has frequency of omega over 2 pi, which is the number of oscillations per unit of time. Now that should look familiar. Remember, our period was 2 pi over the absolute value of b, but when we're talking about simple harmonic motion, we take that period, flip it over, and we get frequency, omega over 2 pi, instead of the absolute value of b over 2 pi. So big start item here, frequency and period. Notice that harmonic motion is sinusoidal with an amplitude, the absolute value of a, and a period of 2 pi over omega. So just swapping out omega, the angular velocity, for our b value. And the frequency is obviously the reciprocal of 2 pi over omega, omega over 2 pi. So they're letting us know frequency is a big deal when you talk about this simple harmonic motion. Example 5, calculating that harmonic motion in a mechanical linkage like the one shown in figure 4.94, a wheel with an 8 centimeter radius turns with an angular velocity of 8 pi radians per second. And it says, what is the frequency of the piston? So the first thing I thought of was when they said angular velocity, that's my omega right there. And yeah, my omega and my W's kind of look the same. I'm going to try to make my W's go inside a little bit there. And what is the frequency of the piston? And we know frequency. And I don't know whether or not, you want to memorize everything all over again, but just remember that omega is B in this situation. So we're going to have omega over 2 pi. And they just told us what omega was. It was 8 pi. So we would have 8 pi divided by 2 pi, which would obviously give us 4. So for what? What is the frequency telling us? And if we go back up, we see it's the number of oscillations per unit of time. So this 4 is telling us that this is going 4 cycles per second. And we can find that unit of time right here with radians per second. So 4 cycles per second. Now, what that would mean graphically, which we see down here in this graph, is that we're really thinking about what the period would need to be. And remember, frequency and period are reciprocals of each other. So the period of this graph would actually be 1/4 of a unit. And in a minute, we're going to look at that graph and think, well, what do we use here to find these positions that they want for part B? So B says, what is the distance from the starting position at t equals 0, exactly 3.45 seconds after starting? So I need to know this. I need to know, well, what was the position at time equals 0? And what was the position at time equals 3.45 seconds, so I can figure out, well, what's the difference between the two? How did all of that work? So what I need to do is think, I need an equation for this thing. So I go back to all of the information that we had up here for calculating harmonic motion, and we need to figure out which of the formulas we would want to use. And so I'm looking at the graph and I see it starts high, and I think, well, that would definitely be cosine. So our directed distance d will equal. And then I remember the a that they had in front of that was supposed to be the radius. And how lucky for us, we have a picture of the circle up here that shows us that the radius is 8. And then we also know the omega piece. They told us that. The period is 8 pi. And where we would normally put an x, in this case, they put a t for time. Now, you probably noticed that when you looked up here. They gave it to us. But we certainly could have written that. And instead of using a t, use an x for time. It wouldn't make any difference at all. The thing we had to get was the formula so that we could figure out where is it when the distance is 0. So if we put a 0 in for the time, we're going to have 8 times the cosine of 0. And then I think about my unit circle. And out here on the unit circle is the point 10. And that's always cosine and then sine. So our cosine is 0. And 8 times 0 will be 0, which makes sense. It hasn't traveled at all at a time of 0, but we need to see that. We need to know where that positioning is. Next up, 3.45. So this one, we're going to use a calculator for. And since we have pi in our information, we're going to need our calculator in radians mode. So there it is, already in radians mode. And I'm going to punch in 8 cosine, and it's nice that those parentheses pop up because we've got a lot to put in there. We've got 8 times pi times 3.45. And we get about 2.472 for that distance. All right, now, how does this have anything to do with this picture that's going on up here? because what's happening is we see that the top of all of this would have to be 8. Notice that our y's are from -10 to 10. So 2, 4, 6, 8. So here's the top of any one of those cycles. And now we've found out that after 3.45 seconds, it's here at y equals 2.472. And what we're supposed to do is figure out how far it's traveled. What is the distance from the starting position? Exactly 3.45 seconds after starting. So we need to subtract those two. 8 minus 2.472, which will be about 5.528 centimeters. And if we stop to do what we really should, which is write a sentence saying, you know, here's everything we found, we would write the piston is approximately 5.528 centimeters from its starting position after 3.45 seconds. Got it. So a basic, do you know what to do to get an equation for this simple harmonic motion? Can you use it by putting in the 0 and the 3.45 to tell the difference between those two positions? Simple harmonic motion. Another example, example 6 here, which reminds me a lot of the little scales that they have at grocery stores. You know, if you want to see how many pounds you have of your oranges, your apples, whatever it may be, before you get up to the till and find out how expensive things are. So we've got calculating harmonic motion, a mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance. Well, we know that's not really the case, but we're going to start there because that'll make it much easier. That can be modeled as harmonic motion. If the weight is displaced a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle. So here we are in the normal position, but the spring can pull it all the way up, or it can go down as far as the spring will stretch. And they're showing that that's going to be 5 units up and down. So what do we need? Well, we need to think, obviously it starts at 0. I mean, that's the normal position, and then it pops up and down from that position. So this one is going to use sine. D equals A sine omega t. Okay, well, what do I know? I know it goes up and down 5, so that's going to be what we would normally consider our amplitude, which in this case is the lowercase a. And they also told me that the period up there is 2 seconds to complete one cycle. That's what period is. So period is 2. And that means the frequency is 1/2. Now, why do I want to know about the frequency? Because the frequency equals omega over 2 pi. And I need that omega. So if I put omega over 2 pi equals 1/2, I can cross multiply and divide by 2 and see that omega equals pi. Well, all I had to have to write this was a, which is 5, and omega, which is pi. That was all I needed to finish that one, because they just wanted me to find a modeling equation. That's the modeling equation right here in the black. D equals 5 sine pi over t. There weren't any follow-up questions. I was ready for follow-up questions, but there weren't any. Just find the model. Now the chapter opener asked us about this, and obviously that was way too early for us to be saying that we know what we're doing about, this is talking about hertz and sound and everything, so now let's take another look at it. If we know that a musical note A above middle C has a pitch of 440 hertz, how can we model the sound produced by it at 80 decibels? Well, first we have to make the connection, and what we need to know is 440 hertz, that's actually the frequency. So where you turn the dial to. And 80 decibels, that's the amplitude, because that's the sound it's making. Decibels measure the intensity of the sound. So there's our amplitude. Now, if I know the frequency, right away I'm thinking omega over 2 pi. Slap a 1 underneath there, make it a proportion. And omega equals 880 pi. And the amplitude would be 80. So we want to figure out a model for this. And since it doesn't say that it starts at a high or a low position, we would absolutely be within our rights to say, I should probably use sine for this then. So amplitude was 80. And our angular velocity, or omega piece in this, was 880 pi. And then we'd put a little t right there. So there's another model. So if we know that a musical note A above middle C has a pitch of 440 hertz, how can we model the sound produced by it at 80 decibels? There it is. Amplitude of 80, frequency of 440, little bit of math, and we end up with a very nice model for that. So that takes care of simple harmonic motion. Like I said, I had hoped that the video would be short, and it was. So there's our 4-8 day 2 assignment. There is a challenge problem here on this page, but we're going to skip that for now, because I definitely want you to just focus on making sure that you understand this simple harmonic motion, and have yourself a great weekend.